Today, my name is Jamie L. Cruz. This will be my quiz 2. Using the double integration method, derive an expression for the maximum value of deflection for the simply supported beam. So as you can see, we have our figure. We have elastic inertia equal constant dy squared y over dx squared is equal to m over elastic inertia. dy over dx is equal to theta. Y is equal to delta. We have our moment 0, m minus wl over 2 times x plus wx times x times x over 2 is equal to 0. Integral x squared times dx m minus wlx over 2 plus wx squared over 2 is equal to 0. So we have our answer to moment wlx over 2 minus w squared over 2. We have our elastic inertia integral d squared y over dx squared equal wlx over 2 minus wx squared over 2 dx theta. Elastic inertia equal dy over dx equal wl over 2 integral of x dx minus w over 2 equal wl over 2 times x over 2 minus w over 2 times x cubed over 3. We have our inertia equal dx over dy equals wlx squared over 4 minus wx cubed over 6 plus ci. Next, as you can see, we have our figure number 2, double integration section AC. mxx equal elastic inertia equal dy over dn equals 0.5 n squared over 6 plus c1. Elastic inertia y is equal to 0.5 n cubed over 6 plus c1 n plus c2. Boundary condition symmetrical loading at C equals low plus 0. 0 equal to 0.5 over 2 times 1 over 2 squared plus C1. C1 is equal to 0.0025 L squared at N equals 0, Y equals 0, C2 is equal 0. Deflection of N equal 1 over 2 equal 0.5 L cubed over 8.6 minus 0.0025 L squared times L over 2. Our answer is YC equals negative 0.02083 over elastic inertia downward. So here, as you can see, we have our area moment method, M over elastic inertia diagram. C minus A equals 1 over 2 times L over 4 times L over 2 times 2 over 3 times L over 2 times I over elastic inertia. We have L cubed over 48 elastic inertia equal to 0.02083 over elastic inertia downward. We have our conjugate beam method. RA plus RB equal 1 over 2 XLX L over Y elastic inertia equal L2 over B elastic inertia. RA equal RB equal L2 over 16 elastic inertia. Deflection at C equal moment at C in conjugate beam equal rad L over 2 minus 1 over 2 times L over Y elastic inertia times L over 2 times L over 2 times 1 over 3 equal L3 over 32 elastic inertia minus L3 over 96. equal L3 over 48 elastic inertia equals 0.0283. We have our next figure. Determine the slope and deflection at point B of the beam shown by double integration method. So we have our figure here. E2 equal constant. E is equal to 10,000 KSI. I is equal to 800 inches to the fourth. Summation moment C equals 0. RAY minus sign represent assume downward. Direction is opposite. Summation forces Y equals 0. RAY plus RCY equals 0. R1Y equal KIPS. In double integration reaction method, we know that elastic inertia equal d squared y over du squared equal mu. Elastic inertia d squared y over du squared equal negative 5u. Integrate the above equation. U, slope equation, elastic inertia dy over du equal minus 5u squared over 2 plus c1. We have our equation 1. Deflection equation, elastic inertia y is equal to negative 5 over 2 times 3 cube over 2 plus c1 u plus c2. We have our equation 2. Begin at a equal u, y equals 0 from 2. C2 is equal to 0 at u, 12 plus 1. Y is equal to 0 from 2. 0 equal negative 5 over 6 times 12 cube plus C1 times 12. We have our sim1 is equal to 120. Slope equation for slope at B, elastic inertia dy over dx equal negative 2.5 u squared plus 120. Theta B equal negative 2.5 u squared plus 120 over elastic 1. Theta B equal 30 over elastic 1 equal 30 times 12 cube over 10,000 times 800. Q over our theta B equal 5.4 times 10 over negative 4 rad. Deflection equation, elastic Y is equal to negative 2.5 u cube over 3 plus 120 u. Deflection at B, u is equal to 16 feet. YB equal negative 2.5 times 63 over 3 plus 120 times 6 over elastic 1. YB is equal to 540 over E2 equal 540 over 10,000 times 800. We have our YB equal 0.11664 inches. For the beam loaded and supported as shown, determine the following: A, rotation at the right support, B, the deflection midspan, the collocation, and the maximum deflection.